Something is passing through our solar system that should not exist in this form, and Japanese scientists are the first to prove it. Right now. 3I Atlas. An interstellar object older than the Sun is moving outward after a precisely measured encounter with Jupiter. Surrounded by an enormous X-ray halo and shedding two distinct tails, recent data from XRISM, Webb, and ALMA reveal unusually high concentrations of methanol and hydrogen cyanide chemicals tied to prebiotic chemistry along with jet behavior that defies standard comet models. With only days left before 3I Atlas fades beyond practical observation after December 19th. This may be our last chance to understand what it really is. If you value clear, evidence-driven science, like the video and subscribe. Now, let's begin. The first detailed high-energy observation of 3I Atlas began quietly, without public attention, but it marked a turning point in how this object would be understood. On November 26, 2025, a Japanese space observatory redirected its instruments toward a region of the constellation Virgo where the interstellar object was moving away from the Sun. The spacecraft was XRISM, short for X-ray Imaging and Spectroscopy Mission, a joint project led by the Japanese Aerospace Exploration Agency with participation from NASA and the European Space Agency. Its purpose is simple in design but demanding in execution to observe the universe in X-rays with enough sensitivity to reveal physical processes that cannot be seen at lower energies. By the time XRISM focused on 3I Atlas, the object had already been inside the solar system for roughly 5 months. During that period, it had repeatedly challenged expectations based on known comet behavior. Optical telescopes showed brightness changes that did not match standard models. Infrared instruments revealed an unusual chemical balance dominated by carbon dioxide rather than water. Radio observations suggested strong, uneven outgassing. Still, none of those findings prepared researchers for what the X-ray data would show. The timing of the observation was tightly constrained. XRISM cannot safely point its detectors too close to the Sun, because direct solar exposure would permanently damage its sensitive instruments. For most of October, 3I Atlas was hidden in the Sun's glare as it passed through perihelion, its closest point to our star. That moment, when heating and activity should have been strongest, was largely inaccessible to detailed spectroscopy. Only solar monitoring spacecraft, designed to look near the Sun, were able to track its overall brightness. Those missions recorded a rapid increase in activity, faster than predicted, but could not determine the chemical or energetic details. By late November, the geometry finally allowed a safe observation window. 3I Atlas had emerged far enough from the Sun's direction in the sky, and XRISM's team scheduled a continuous exposure lasting 17 hours. During that time, the X-ray telescope collected individual photons arriving from the region around the comet, building a faint but measurable signal. When the data were processed, the result was unexpected. Instead of a compact source near the nucleus, researchers saw a diffuse glow extending outward across an angular distance of about 5 arc-minutes. At the comet's distance from Earth, that angular size translates to a physical scale of roughly 400,000 kilometers. For comparison, the average distance between Earth and the Moon is about 384,000 kilometers. In other words, the X-ray emitting region around 3I Atlas appeared larger than the gap separating our planet from its only natural satellite. This finding immediately stood out because no interstellar comet had ever been confirmed as an X-ray source before. X-ray emission from comets within our own solar system has been known since the late 1990s. when Comet Hyakutake surprised astronomers by glowing at high energies. That discovery led to a well-established explanation known as charge exchange. The solar wind, a steady flow of charged particles streaming outward from the sun, carries highly ionized atoms. When these ions collide with neutral gas atoms in a comet's coma, they can capture electrons. As the electrons settle into lower energy states, X-ray photons are released. The process is efficient and produces a soft X-ray glow that traces the interaction between the comet's gas and the solar wind. For comets formed in our solar system, this mechanism is familiar. Their ices have been repeatedly warmed and altered by the sun over billions of years. Their gas output and composition fall within a range that models can reproduce reasonably well. 3I Atlas is different in a fundamental way. It did not form around the sun. It likely condensed around another star billions of years ago, possibly as early as 7 billion years in the past, long before our solar system existed. Until its recent passage, the ices locked in its nucleus had never been heated by our star. The gases now escaping from its surface carry chemical signatures shaped by an entirely different stellar environment. Because of this, researchers had an open question long before the X-RISM observation. Would an interstellar comet interact with the solar wind in the same way as local comets? Or would its unfamiliar chemistry and structure produce a different outcome? The initial analysis suggests that the observed X-rays are associated with a large, diffuse cloud of gas surrounding the nucleus, consistent with charge exchange taking place on a much larger scale than usual. This interpretation aligns with earlier observations at other wavelengths. Infrared data from the James Webb Space Telescope, along with measurements from the Sphere-X mission, revealed a massive plume of carbon dioxide extending hundreds of thousands of kilometers into space. Those observations indicated that the comet was releasing gas at an exceptional rate. Based on Webb's measurements, 3I Atlas was emitting on the order of 129 kilograms of carbon dioxide every second, along with smaller but significant amounts of water and carbon monoxide. That continuous flow of gas provides abundant material for interactions with the solar wind, creating the conditions needed for X-ray production. At the same time, the X-RISM team has emphasized caution. In their preliminary notice released on December 3rd through the Astronomer's Telegram, they noted that certain instrumental effects can sometimes create features that resemble extended emission. One such effect is vignetting, a gradual drop in sensitivity toward the edges of the detector's field of view. Detector noise can also introduce faint structures that are not astrophysical in origin. Because of this, additional analysis is required to confirm that the observed halo truly originates from the comet and not from the measurement process itself. This careful approach reflects a core principle of science. Extraordinary results require thorough verification. Even so, early indications suggest that the detection is real. The structure appears centered on the comet's position, and its scale matches expectations based on the known extent of the gas plume. If confirmed, the X-ray spectrum itself becomes a valuable source of information. Charge exchange produces characteristic emission lines that depend on which ions and neutral atoms are involved. Preliminary signals point to X-ray energies associated with carbon, nitrogen, and oxygen ions. These elements are not chosen arbitrarily. They form the basic framework of organic chemistry and are central to the molecular processes that underlie life as we understand it. The significance here does not lie in speculation about biology, but in chemistry, an object that has traveled between stars for billions of years, carrying frozen material from a planetary system we cannot observe directly, is now interacting with the sun's particle wind in a way that makes its elemental makeup visible at high energies. In a literal sense, 3I Atlas is revealing its chemical identity across parts of the electromagnetic spectrum that have only recently become accessible with modern instruments. The timing of this detection adds another layer of importance. 3I Atlas reached perihelion on October 29th, at a distance of about 203 million kilometers from the Sun. During that passage, Earth-based telescopes were effectively blind to its detailed behavior because of its proximity to the Sun in the sky. This meant that the period of maximum heating and likely peak activity could not be studied with high-resolution spectroscopy. Solar missions such as Stereo and SOHO tracked its brightness during that interval and observed a rapid surge. But they could not determine which gases were responsible or how the comet's structure responded in detail. Now, as the comet moves away from the Sun and heads back toward interstellar space, it remains highly active. Gas and dust continue to stream from its nucleus, and the object will stay observable for several more months. The X-ray detection opens a new way to study this activity. If charge exchange is indeed responsible for the glow, then changes in the solar wind should produce corresponding changes in the X-ray brightness and spectrum. In effect, there is an ongoing interaction between our star and this ancient visitor, recorded in high-energy photons that researchers are only beginning to decode. Each photon detected carries information not just about conditions near the comet, but also about the environment in which its materials formed. They reflect processes around a star that may no longer exist, within a planetary system that has long since dispersed. In that sense, 3I Atlas acts as a physical record, preserving chemical details from a distant and inaccessible part of the galaxy. The X-RISM team has indicated that additional observations are planned as data processing techniques improve. With more refined spectra, it may become possible to identify which elements dominate the X-ray emission and to compare those findings directly with results from infrared and radio telescopes. Such comparisons could reveal whether the chemistry inferred from high-energy interactions matches the chemistry measured through molecular vibrations and rotational transitions at lower energies. If they align, it would strengthen the idea that the building blocks of complex chemistry are distributed widely across planetary systems, regardless of where they form. This X-ray discovery also fits into a broader pattern that has emerged since 3I Atlas was first identified. Repeatedly, predictions based on familiar solar system comets have fallen short. When Webb observed its composition in August, the ratio of carbon dioxide to water turned out to be nearly 8:1, among the highest values ever measured for a comet. As it approached perihelion, its brightness increased more rapidly than standard thermal models anticipated. When observers expected a single tail pointing away from the Sun, the comet developed an additional sunward-facing structure that did not have an obvious explanation. Now, there is evidence for X-ray emission extending hundreds of thousands of kilometers into space, suggesting that whatever process drives this comet's activity is energetic enough to produce detectable signals across a wide range of wavelengths. Taken together, these observations form a consistent picture. 3I Atlas does not fit neatly into existing categories derived from solar system experience. Some researchers interpret this as a sign that interstellar comets are simply more diverse than previously assumed. The galaxy contains stars with a wide range of masses, radiation environments, and chemical histories. Icy bodies formed in those systems could reasonably differ in composition and structure from those formed around the Sun, over billions of years drifting between stars. Exposure to cosmic radiation could further alter surface chemistry, breaking molecular bonds and creating new compounds that behave differently when heated. At this stage, that conservative explanation remains sufficient. It does not require new physics or non-natural origins. It does, however, require an expansion of existing models to account for a broader range of starting conditions. 3I Atlas serves as a reminder that the small sample of comets in our own solar system may not represent the full diversity of icy bodies in the galaxy, and that the first interstellar visitors we observe are likely to challenge assumptions built on local experience. Recent analysis has raised the possibility that 3I Atlas no longer presents its original surface to us at all. One study suggests that during its roughly 7 billion-year journey through interstellar space, the comet may have developed a thick, radiation-processed crust. Over such immense timescales, constant exposure to cosmic rays and high-energy particles can alter the structure of ice and embedded compounds, breaking molecular bonds and forming new materials. If this has happened, the outer layers we now observe may differ greatly from the pristine substances that condensed when the comet first formed around another star. In that case, some of its unusual behavior may reflect long-term chemical evolution rather than conditions in its birthplace. Not all researchers are fully satisfied with that explanation. As observations have accumulated, a growing number of astronomers, including those working well within the scientific mainstream, have acknowledged that 3I Atlas presents a cluster of open questions that deserve careful attention. This is not a claim of anything artificial, nor a rejection of natural processes. It is an admission that current models of cometary behavior, built almost entirely on experience within our own solar system, may be incomplete when applied to objects that formed elsewhere and evolved in isolation for billions of years. The X-ray halo detected by XRISM is the latest entry in a steadily expanding record of anomalies, and it highlights a familiar pattern in science. Progress often begins when observations resist easy explanation. Follow-up observations with XRISM are scheduled to continue over the coming weeks. Of particular interest is its high-resolution X-ray spectrometer known as RESOLVE. If the emission remains bright enough, RESOLVE may be able to separate individual spectral lines with much greater precision, offering clearer clues about which elements dominate the outflow. At the same time, telescopes operating at other wavelengths are continuing their own measurements, building a layered, multi-instrument picture of the comet before it retreats farther from the Sun and gradually fades into the outer solar system. This coordinated effort reflects an understanding shared across the community. The window to study this object in detail is limited, and once it closes, 3I Atlas will not return. Even so, the X-ray halo is only one part of a much larger puzzle. While Japanese scientists were still processing their late November data, another spacecraft had already obtained images that revealed a different and equally intriguing feature. When the European Space Agency's Jupiter Icy Moons Explorer, commonly known as JUICE, turned its navigation camera toward 3I Atlas, it recorded a view that challenged simple expectations. Instead of a single tail streaming away from the nucleus, the images showed two distinct structures extending in different directions, one of which appeared to consist of material not immediately anticipated from earlier models. As of December 11, 2025, the timing of these observations has taken on added importance. In exactly 8 days, on December 19th, 3I Atlas will reach its closest point to Earth. The term closest can sound alarming when applied to an interstellar object, but in this context, it is purely relative. The comet will pass at a distance of about 1.8 astronomical units, which corresponds to roughly 170 million miles, or about 270 million kilometers. That is nearly twice the average distance between Earth and the Sun. Orbital mechanics leave no room for ambiguity here. There is no impact scenario and no physical risk to our planet. What does change with proximity is observational opportunity. The closer the comet is, the more light reaches detectors. The finer the details that can be resolved, and the more information can be extracted before the signal weakens. For that reason, December 19th marks a critical inflection point in the scientific study of 3I Atlas. After this date, the comet will continue outward on its hyperbolic path, growing fainter week by week as it recedes. Each additional observation will require more effort, longer exposures, and more careful filtering of noise. What is learned in the weeks surrounding closest approach may well constitute the most complete record humanity ever obtains of this particular visitor from another star. At present, the comet lies in the constellation Virgo and is visible in the pre-dawn sky from the northern hemisphere. Its apparent brightness is around magnitude 12, far too faint for the naked eye, but within reach of large amateur telescopes under dark conditions. Through an eyepiece, it appears as a diffuse patch of light with a brighter central region, surrounded by a soft, extended coma. Long exposure photographs reveal the tail structures that have drawn so much attention, though their visibility depends strongly on viewing geometry and observing conditions. As December progresses, the comet's position in the sky improves, moving farther from the sun's glare and becoming accessible for longer periods each night. This gradual shift has prompted observatories around the world to prepare for an intensive final phase of data collection. In effect, the solar system has become a distributed observatory, a wide array of missions, each designed for different purposes, has been redirected or adapted to contribute observations. Near Earth, the Hubble Space Telescope continues to monitor the comet with its Wide Field Camera 3, delivering high-resolution images of the inner coma and tail regions. The James Webb Space Telescope has additional infrared observations scheduled to track how the carbon dioxide-rich coma evolves as solar heating decreases. The SphereX mission, an all-sky infrared surveyor launched earlier in the year, has already provided crucial measurements of the comet's chemical fingerprint. Beyond Earth orbit, other spacecraft offer perspectives that ground-based telescopes cannot match. NASA's Psyche mission, currently traveling toward a metal-rich asteroid, observed 3I Atlas in September when the spacecraft passed within about 33 million miles of the comet. Those images helped refine the object's trajectory with unusual precision. The Lucy mission, designed to study Jupiter's Trojan asteroids, captured views from a distance of roughly 240 million miles, adding geometric constraints that improve orbital modeling. Mars has also played an important role. During the comet's passage near the Red Planet on October 3rd, when it came within about 29 million kilometers of Mars, both the Mars Reconnaissance Orbiter and the ExoMars Trace Gas Orbiter conducted observations. The high-resolution camera aboard the Mars Reconnaissance Orbiter was capable of imaging the comet at scales of about 30 kilometers per pixel, although only selected data have been released publicly. These observations add another independent vantage point to the growing archive. Even the Perseverance rover on the Martian surface contributed measurements, extending the observational baseline across interplanetary space. Solar monitoring missions have filled in gaps that no other platforms could cover. Spacecraft such as Stereo, SOHO, and the newer Punch mission tracked the region around the Sun continuously during the period when 3I Atlas was invisible from Earth. They recorded the comet's rapid brightening as it passed through perihelion, documenting the intensity of its response to solar heating. The Parker Solar Probe, humanity's closest spacecraft to the Sun, may also have gathered relevant data, though no public confirmation has been made. Among all these efforts, JUICE occupies a special position. Launched in April 2023, the spacecraft is following a complex trajectory that will eventually deliver it to Jupiter in 2031. In early November, JUICE found itself about 41 million miles from 3I Atlas, closer than any other operational probe at that time. Crucially, this geometry placed the spacecraft in direct view of the comet just days after perihelion. When activity was rising sharply, the JUICE team activated 5 scientific instruments during this encounter. Janus, the optical camera, provided visible light imaging, MIAS and UVS. Spectrometers covering different wavelength ranges analyzed reflected and emitted light. W, a submillimeter wave instrument, probed cold gas components, while PEP, a particle detector, searched for charged material flowing away from the nucleus. In addition, the spacecraft's navigation camera was pointed toward the comet, a decision that would yield an unexpectedly informative result. At the time, JUICE was operating under significant constraints. To protect its instruments from intense solar radiation during its inner solar system cruise, the spacecraft uses its main high-gain antenna as a heat shield. As a consequence, data transmission to Earth is limited to a smaller medium-gain antenna, reducing the flow of information to a fraction of normal rates. The complete scientific dataset from the November observations will not reach Earth until February 2026. Faced with this delay, mission controllers had to choose between waiting months for the full picture or downloading a small preview. They chose to look early. What arrived was only 1/4 of a single image from the navigation camera. Captured on November 2nd, 2025. Even at low resolution and partial coverage, the image was striking. 3I Atlas appeared surrounded by a bright coma, with 2 distinct tail structures extending in different directions. One tail, composed of ionized gas interacting with the solar wind, stretched upward in the frame. A second, fainter tail, made of fine dust particles, curved away toward the lower left. The comet appeared intensely active, still energized by its recent close passage to the Sun. In principle, the presence of 2 tails is not unusual. Many comets display both a dust tail and an ion, or plasma, tail when conditions are right. Solar radiation pressure acts on dust grains, pushing them away from the nucleus along curved paths shaped by gravity and light. At the same time, the solar wind sweeps up ionized gas and carries it directly away from the Sun, forming a straighter structure. These processes act on different materials and naturally produce separate features. What surprised researchers was the clarity and strength of both tails in an image taken by a camera designed primarily for navigation rather than detailed comet science. Earlier in its journey, 3I Atlas had appeared to lose its tail altogether in some observations, prompting speculation that something unusual was occurring. Later analysis showed that this apparent disappearance was a matter of perspective. For a time, the tail was oriented almost directly away from Earth, hidden behind the bright coma, much like looking straight into the beam of a flashlight. As viewing geometry changed, the tail became visible again. The JUICE image confirms that the comet is behaving like a highly active natural object. Exactly what would be expected from an icy body experiencing its first intense solar heating in billions of years. The vigorous outgassing observed elsewhere, including cryovolcanic eruptions that eject material from the surface, feeds both the gaseous coma and the population of solid particles that form the dust tail. Taken together, these observations present a coherent picture of a comet under extreme thermal stress. Still, Important details remain unresolved. The precise composition of the tails, the ratio of dust to gas, the size distribution of particles, and the exact chemistry of the ionized material cannot be determined until the complete JUICE dataset arrives. For now, those answers remain deferred, waiting in data that will not be fully available until February 2026, when the remaining observations from JUICE finally arrive. They will represent the closest and most detailed view of an interstellar comet ever obtained by a spacecraft. This was never part of the mission's original plan. JUICE was designed to study Jupiter's icy moons Ganymede, Callisto, and Europa, not visitors from other star systems. Its instruments were built to analyze frozen surfaces, tenuous atmospheres, and magnetic interactions deep within the Jovian system. That the spacecraft happened to be in position to observe 3I Atlas during one of the comet's most active phases is a coincidence shaped entirely by orbital mechanics. It is a rare alignment of trajectories, and researchers are working quickly to extract as much information as possible from it. The sense of urgency is widely shared as the calendar moves toward December 19, 2025. The comet approaches its closest point to Earth, while the full JUICE dataset remains weeks away from transmission. Even then, once those data arrive in early 2026, they will describe only a brief moment in the object's passage. 3I Atlas is moving through the solar system at roughly 130,000 miles per hour, carrying frozen material that has remained locked away since long before the Sun existed. Its encounter with our planetary neighborhood will be short. Afterward, it will continue outward, fading steadily as it returns to interstellar space. What is not measured during this narrow window will be lost permanently. That reality shapes every decision now being made, despite the gaps that remain. Some of the most consequential findings about 3I Atlas have already emerged. And they come not from images, but from chemistry. Measurements taken over the past several months show that the molecular composition of this comet is unlike anything previously observed. Certain compounds appear in concentrations far higher than those seen in comets formed around the Sun. These molecules are not obscure or incidental. They are directly connected to chemical pathways that, on Earth, are associated with the origins of life. The announcement released by NASA regarding methanol and hydrogen cyanide has drawn careful attention, not because it implies biology, but because it forces a reassessment of how common life-related chemistry may be throughout the galaxy. Those measurements were made using the Atacama Large Millimeter Submillimeter Array, known as ALMA, high in the Chilean Andes. At an altitude of about 5,000 meters, 66 radio antennas operate together as a single instrument. Unlike optical telescopes, which collect visible light reflected or emitted by objects, ALMA detects radiation at millimeter and submillimeter wavelengths. These wavelengths are especially sensitive to cold molecules in space. Each molecule emits radiation at specific frequencies, producing a distinct spectral signature. In effect, ALMA does not take pictures of objects so much as it identifies their chemical ingredients. In late 2025, ALMA focused on 3I Atlas during its approach toward perihelion. A team led by Martin Cordner at NASA's Goddard Space Flight Center observed the comet multiple times between August and October, searching for molecules that could reveal the chemical environment in which the comet originally formed. The results went well beyond expectations. One of the most striking findings was the rate at which the comet was releasing methanol. Measurements indicate a production rate of approximately 40 kilograms per second. Methanol is the simplest alcohol molecule. It consists of one carbon atom bonded to 4 hydrogen atoms and 1 oxygen atom in a specific arrangement. In comets from our own solar system, methanol is typically present only in small amounts, a minor component compared to water ice in 3I Atlas. However, methanol makes up roughly 8% of the total gas being released. That proportion is about 4 times higher than what is normally measured in solar system comets. In terms of both absolute production rate and relative abundance, the methanol levels observed in this object rank among the highest ever recorded. Methanol was not the only molecule detected. ALMA also measured the presence of hydrogen cyanide flowing from the comet's nucleus at rates between roughly 1/4 and 1/2 of a kilogram per second. Hydrogen cyanide occupies a complicated place in chemistry. In high concentrations, it is toxic. At the same time, it plays a crucial role in laboratory pathways that produce amino acids and nucleic acid bases, the fundamental components of proteins and genetic material. The chemistry enabled by hydrogen cyanide is central to many models of prebiotic synthesis. What stands out in the ALMA data is not just the presence of these molecules, but their relationship to one another. The ratio of methanol to hydrogen cyanide in 3I Atlas is unusually high. According to analyses discussed by astronomers including Avi Loeb, this ratio rivals the most extreme values ever observed. Previously, such enrichment had been seen only in a small number of anomalous comets within our own solar system. Most notably, Comet C 2016 R2. That object was long considered a rare outlier, difficult to explain within existing frameworks. The arrival of 3I Atlas, originating from an entirely different star system and displaying a similar chemical pattern, suggests that such compositions may not be as unique as once thought. To understand why this matters, it helps to compare these findings with what is typical closer to home. In most solar system comets, hydrogen cyanide and methanol appear only in trace amounts. Water dominates the volatile inventory by a wide margin. The chemistry observed in 3I Atlas is not just different in degree, but different in direction. The enrichment points toward molecules that participate directly in prebiotic chemistry, compounds that experiments have shown can lead to more complex organic structures under the right conditions. This does not imply intent or design. It reflects the conditions under which the comet's material formed and evolved. ALMA's observations also revealed an important spatial detail. Methanol emission was detected not only near the comet's solid nucleus, but throughout the surrounding coma. This indicates that icy grains dispersed into the cloud of gas and dust are themselves releasing methanol as they warm in sunlight. Such a distributed source suggests that volatile compounds are embedded throughout the comet's structure, rather than being confined to a single central reservoir. The object appears to be chemically rich from surface to interior, a frozen archive of complex material. These findings have sometimes been simplified in public discussions, leading to headlines that imply far more than the data supports. 3I Atlas is not carrying life, and there is no evidence that it could deliver living organisms to Earth. What the observations show is something both more modest and more important. Material formed around another star contains elevated concentrations of molecules that are relevant to the chemistry of life. That distinction matters. It shifts the focus from biology to chemistry, from speculation to measurement. One of the central questions in astrobiology concerns how common the chemical conditions for life may be. If the mixture of molecules present in the early solar system was a rare outcome of unusual circumstances, then life might be scarce elsewhere. If similar chemical inventories are widespread, then the emergence of life could be a common consequence of planetary formation. 3I Atlas provides a valuable data point. It formed around a different star, possibly 7 billion years ago. Potentially in an older region of the Milky Way, where stellar chemistry differs from our local neighborhood. Yet, it carries abundant methanol and hydrogen cyanide. That suggests that the raw materials for prebiotic chemistry are not confined to one place or one epoch. This observation connects naturally to long-standing discussions about panspermia. The idea that life or its precursor chemistry might spread between planetary systems carried by comets, asteroids, or dust. In its strongest forms, panspermia has often been viewed with skepticism. However, the chemical aspect of the idea that complex organic molecules can be transported across space is well supported. Laboratory experiments and space observations show that many such molecules can survive harsh interstellar conditions. We also know that early Earth experienced heavy bombardment by comets and asteroids roughly 4 billion years ago. What remains uncertain is how much those deliveries contributed to the chemical pathways that eventually led to living systems. 3I Atlas does not answer that question, but it demonstrates that interstellar delivery of relevant molecules is physically possible. There is another dimension to these findings that bears on the comet's internal structure. The way methanol and hydrogen cyanide are being released suggests that 3I Atlas is not chemically uniform. Different regions may contain different mixtures of ice and minerals, responding differently as heat penetrates the surface. Some researchers have proposed that such patchiness could indicate a higher metal content within parts of the nucleus. In known chemical systems, reactions between water, heat, and iron-bearing minerals can produce methanol. If the comet's interior contains iron-rich material, warming near perihelion could have triggered active chemical reactions, generating methanol in real time rather than simply releasing ancient ices. If this interpretation proves correct, 3I Atlas would offer a rare opportunity to observe ongoing chemistry within a comet, not just passive sublimation. The object would function as a natural laboratory, showing how solar energy can drive chemical transformation in icy bodies. Similar processes may have occurred on the early Earth, where heat, water, and minerals interacted over long periods. Observing such reactions in space provides context for understanding those ancient terrestrial environments. Further ALMA observations are planned as the comet continues its outward journey. Researchers will track how production rates of methanol and hydrogen cyanide change as solar heating decreases. So far, the data show that methanol output increased sharply as the comet approached the Sun as it recedes. That trend will be tested in reverse. If sublimation alone governs the behavior, production should decline smoothly with distance. If more complex chemistry is involved, deviations may appear. Other observatories are contributing complementary information. Infrared instruments on the James Webb Space Telescope can detect molecular species that radio telescopes cannot. Ground-based facilities are monitoring visible emission lines that trace specific atoms and reactive fragments in the coma. Together, these efforts are assembling a chemical inventory piece by piece. The picture is still incomplete, but it is already clear that 3I Atlas occupies a category of its own. This comet does not challenge known physics, and it does not require artificial explanations. What sets it apart is its origin. It formed in conditions that have never been sampled directly before, carrying the chemical imprint of a distant and long-vanished environment. As data continue to arrive, 3I Atlas is revealing not how strange the universe is, but how much broader it may be than the narrow slice we have known until now. Every comet native to our solar system, no matter how unusual its behavior may appear, shares a common origin. all of them formed within the same disk of gas and dust that surrounded the young sun more than 4.5 billion years ago. Their differences reflect local conditions within that disk, but their chemical foundations are related. 3I Atlas does not belong to that family. It is a genuine outsider, an object that formed around another star and entered our solar system only recently. Its chemistry reflects conditions that existed far beyond our neighborhood, and that distinction gives its measurements special weight when astronomers report that this comet contains ingredients relevant to life. They are not making symbolic or philosophical claims. They are describing specific molecules and well-understood chemical reactions. Methanol can be converted into formaldehyde, a compound that plays a key role in the formation of simple sugars. Hydrogen cyanide can link together through known reactions to form adenine, one of the 4 nucleobases found in DNA. These pathways are not speculative. They have been demonstrated repeatedly in laboratory experiments under conditions meant to resemble early planetary environments. Similar reactions may have taken place on the early Earth, and there is no physical reason they could not occur on other worlds as well. In that sense, 3I Atlas functions as a chemical messenger. The information it carries is encoded not in signals or structures, but in molecules. Those molecules indicate that the chemistry associated with life is not restricted to a single planetary system. Instead, it appears to be distributed across the galaxy, frozen into icy bodies that occasionally pass through star systems like our own. When such objects encounter planets, they can deliver their chemical cargo, adding complexity to local environments. This does not imply intent or design. It reflects the way matter circulates on cosmic scales. While these chemical findings are significant, they do not stand alone. At the same time that ALMA was measuring methanol and hydrogen cyanide, other observers were documenting physical behavior that challenged simplified models of comet activity. The eruptions of gas and dust from the surface of 3I Atlas, sometimes described as cryovolcanic outbursts, appeared uneven and intense. These patterns suggested internal dynamics that are not easily captured by basic assumptions about uniform icy bodies slowly warming in sunlight. The chemistry raised questions about origin. The behavior raised questions about structure. One of the clearest pieces of evidence for that activity came from the JUICE mission. In early November of 2025, the spacecraft completed its planned observation window for 3I Atlas. During that period, 5 scientific instruments were directed toward the comet, collecting spectra, images, and particle measurements during one of its most energetic phases. Those observations may ultimately represent the most detailed close-range dataset ever obtained for an interstellar object. Yet all of that information remained aboard the spacecraft, unable to reach Earth immediately. The limitation was not a failure of planning, but a consequence of thermal engineering. JUICE was designed to operate near Jupiter, where it must tolerate sharp temperature contrasts between deep shadow and intense reflected sunlight. To reach that distant destination, the spacecraft must first travel through the inner solar system, using a series of gravitational assists. During these passages close to the Sun, protecting sensitive electronics becomes a priority. Engineers solved this by orienting the spacecraft so that its large, high-gain antenna faced the Sun, using the dish as a heat shield. The approach worked, but it came at a cost. With the high-gain antenna pointed sunward, JUICE could not use it to transmit data to Earth. Communication was limited to a smaller, medium-gain antenna, capable of sending only a fraction of the normal data rate. The result was a bottleneck. The complete science dataset from the 3I Atlas observations could not be transmitted until orbital geometry allowed the spacecraft to rotate safely, a window that would not open until February 2026. That meant a delay of several months for data that might be historically significant. The mission team chose not to wait without any feedback. Instead, they made a careful decision to download a small portion of the data as a preview. They selected a fraction of a single image from the navigation camera, enough to confirm that the observation had succeeded and to offer a preliminary look at the comet's state. This was not intended as a substitute for the full dataset, but as a verification step. On December 4th, 2025, the European Space Agency released that partial image. Even with limited resolution and incomplete coverage, it provided valuable information. 3I Atlas appeared bright and clearly active. Its nucleus was surrounded by an extended coma, indicating substantial outgassing. Most strikingly, two distinct tail structures were visible against the background of stars. One of these was a plasma tail, composed of ionized gas interacting with the solar wind. In the image orientation, it extended upward, aligned with the direction set by charged particles flowing outward from the sun. The second was a dust tail, fainter and curved, formed by solid grains released from the nucleus and pushed gently by sunlight. The presence of both features confirmed that the comet was emitting gas and dust simultaneously, a hallmark of vigorous cometary activity. From a physical standpoint, this behavior is well understood. When sunlight heats a comet's surface, volatile ices transition directly from solid to gas. Some of that gas becomes ionized by solar ultraviolet radiation and is then carried away by the solar wind, forming a relatively straight plasma tail. Dust particles released alongside the gas experience radiation pressure that depends on their size, causing them to follow curved paths. Smaller grains are pushed more strongly than larger ones, producing a broad dust tail with a different shape. Many solar system comets display this dual structure under favorable conditions. What makes this observation important is not that two tails exist, but that they exist on an interstellar comet. 3I Atlas formed in a protoplanetary disk around another star, where chemical abundances and grain properties may have differed significantly from those in our own system. The ice within its nucleus condensed under those conditions, trapping dust with potentially different compositions and size distributions. Seeing familiar tail structures tells us that despite those differences, the basic physics of cometary activity is universal. Solar radiation and the solar wind interact with interstellar ice in the same fundamental way they interact with local ice. The timing of the image adds further context. It was captured on November 2nd, just 4 days after perihelion. At that moment, 3I Atlas was still responding to the thermal shock of its closest approach to the Sun. For most of its existence, the comet drifted through interstellar space, where temperatures remain only a few degrees above absolute zero. Its ices stayed frozen and chemically stable for billions of years. Then, over the course of a few months, solar energy penetrated the surface, warming layers that had never experienced such conditions before. As temperatures rose, volatile compounds began to sublimate rapidly. Gas expanded outward at speeds of hundreds of meters per second, entraining dust grains and carrying them into space. The process was not explosive in the everyday sense, but it was dramatic on astronomical scales. The nucleus released material at a high rate, creating a bright coma and extended tails. The partial juice image captured this release in progress, offering a snapshot of a transition from deep freeze to intense activity. There is a practical significance to this observation. Some had wondered whether the intense solar heating near perihelion might disrupt or fragment the nucleus, reducing activity afterward. The image showed no such collapse. Instead, it confirmed that the comet remained intact and active, continuing to shed both gas and dust. That confirmation helps anchor interpretations of data from other observatories, providing a reference point for brightness measurements, spectral analysis, and models of mass loss. The circumstances under which this image was obtained underscore how contingent such discoveries can be. JUICE was not designed to study comets, let alone interstellar ones. Its navigation camera exists to support spacecraft orientation, not to perform detailed scientific imaging. Yet a combination of timing, trajectory, and engineering choices placed the spacecraft in position to document a phenomenon no other probe had observed at comparable proximity: small changes in arrival time, orbital geometry, or thermal constraints could have eliminated the opportunity entirely. When the full dataset arrives in February 2026, researchers will be able to move beyond confirmation and into detailed analysis. Spectra from the MAJAs and UVS instruments may identify specific molecular species in the coma with far greater precision. The submillimeter instrument SWI could reveal the presence of water vapor and other volatiles. The particle detector PEP may have sensed charged material flowing through the spacecraft's environment. Each instrument contributes a different perspective, and together they will form a more complete picture of the comet's composition and activity, even without those data. The partial image has already advanced understanding. It verified that 3I Atlas behaved like an active comet through perihelion. It demonstrated that an interstellar object can display the classic morphology associated with cometary physics. And it provided a clear example of how familiar processes operate on material formed far beyond the sun's influence. Public reaction to the image was immediate. Once released, it circulated widely, accompanied by interpretations ranging from careful scientific commentary to unfounded speculation. Some observers claimed the dual tail structure looked unlike any comet, despite the fact that such structures are well documented under appropriate conditions. Others suggested artificial features in the coma, conclusions that image processing specialists quickly traced to artifacts introduced by partial data and enhancement techniques. These responses highlighted the gap between visual impression and physical explanation. For scientists, the value of the image lies not in how striking it appears, but in what it confirms. 3I Atlas remains a natural object governed by known forces. At the same time, it continues to challenge assumptions by presenting combinations of chemistry, structure, and activity that have not been observed together before. Each confirmed measurement narrows uncertainty while revealing new questions. As additional data arrive, those questions will shift from speculation to analysis, grounded in evidence collected during a brief and unrepeatable encounter. Speculation about artificial origins continues to circulate, even as the evidence for natural processes grows stronger. Each new observation of 3I Atlas is quickly reinterpreted by some through a lens of suspicion. The dual tails become framed as signs of controlled propulsion. The bright coma is described as an energy field. High activity levels are recast as intentional signaling. These interpretations persist not because the data support them, but because extraordinary objects invite extraordinary narratives. The problem is not curiosity, it is distraction. What we are observing is already remarkable without invoking anything beyond physics. An object formed around another star is passing through our solar system close enough to be photographed by a spacecraft built to explore Jupiter. Its chemistry reflects conditions from an alien protoplanetary disk. Its structure responds to sunlight and solar wind in ways that confirm physical laws apply across stellar systems. Its brightness reveals reservoirs of volatile material that survived billions of years of interstellar cold. None of this requires non-natural explanations. The wonder lies precisely in the fact that familiar processes are operating on unfamiliar material. The JUICE mission team deserves recognition for recognizing this opportunity and acting quickly. When 3I Atlas was discovered in July, planners immediately evaluated whether observation was feasible given the spacecraft's trajectory, thermal limits, and communication constraints. They identified a narrow window in early November and committed to it, fully aware that most of the data could not be transmitted until months later. The partial navigation camera image was never meant to be definitive. It was a confirmation that the gamble had paid off and a preview of what the full dataset might contain once transmission becomes possible in February 2026, while JUICE awaits that transmission window. Other observatories continue their work. The Hubble Space Telescope has captured multiple images since the comet emerged from the sun's glare, tracking changes in coma size and tail extent over time. The James Webb Space Telescope is preparing follow-up infrared observations to monitor how carbon dioxide and other volatiles evolve as the comet recedes and solar heating weakens. Ground-based telescopes around the world are contributing nightly photometric and spectroscopic measurements whenever conditions allow. Together, these efforts form a coordinated global campaign, designed to extract as much information as possible before distance and fading brightness make further study impractical. As this broader dataset grows, it continues to reveal behavior that demands careful physical explanation. The twin tails documented by JUICE are not static features. They are fed by active processes occurring on the comet's surface. Processes that researchers increasingly describe as cryovolcanism. This activity points to internal dynamics more complex than simple uniform heating of an icy body. Cryovolcanism refers to volcanic-like eruptions driven not by molten rock, but by volatile ices. The term may sound unusual, but the phenomenon is well established within our solar system. On Saturn's moon Enceladus, jets of water ice erupt hundreds of kilometers into space from fractures near the South Pole. On Neptune's moon Triton, nitrogen ice erupts in towering plumes observed by passing spacecraft. Pluto shows geological features consistent with ancient cryovolcanic activity as well. In all these cases, cold bodies composed largely of ice experience eruptions when internal pressure builds and finds a pathway to escape. The materials differ from terrestrial volcanoes, but the underlying physics is similar. On a comet, the mechanism begins with solar heating. As sunlight warms the surface, heat conducts inward toward deeper layers that have remained frozen. When buried volatile compounds reach their sublimation temperature, they transition directly from solid to gas. This transformation increases pressure beneath the surface. If the gas encounters a fracture, porous region, or structural weakness, it escapes rapidly, carrying dust and ice particles with it. The result is a focused jet rather than diffuse outgassing. Rotation adds an important layer of complexity. As a comet spins, specific surface regions cycle between sunlight and shadow. A vent exposed to sunlight may erupt vigorously, then quiet as rotation carries it into darkness. Hours later, as the same region returns to sunlight, activity resumes. This on-off pattern produces periodic behavior tied directly to the rotation of the nucleus. Observations of 3I Atlas suggest exactly this process is underway. In early December, a team of European researchers led by Josep Trigo Rodriguez at the Institute of Space Sciences in Barcelona reported structured jet features extending from the nucleus. These were not uniform plumes spreading evenly in all directions. They were collimated streams emerging from discrete source regions, maintaining coherence over distances of hundreds of thousands of kilometers before dispersing into the surrounding coma. The most striking aspect of these features was their spiral shape. Such spirals form naturally when material is ejected from a rotating body. As the nucleus spins, a jet sweeps through space, tracing a curved path over time. Long exposure images capture this motion as a spiral or arc pattern. The geometry of the spiral encodes information about the rotation period of the nucleus. By measuring how far the pattern advances over a known time interval, researchers can estimate how fast the comet is spinning. Early analyses suggest that 3I Atlas may have a rotation period on the order of several hours. These estimates remain uncertain, influenced by the three-dimensional orientation of the jets and the viewing angle from Earth. Continued monitoring over the coming weeks is expected to refine these values. Even at this stage, the presence of coherent spiral jets indicates that activity is localized and rotationally modulated, not random. The locations of these jets offer further insight. Cryovolcanic vents do not form arbitrarily. They emerge where subsurface volatiles are present and where structural pathways allow gas to escape. If the same regions repeatedly produce jets as the comet rotates, it implies an internal structure that is heterogeneous. Some areas are rich in volatile ices and actively venting. Others may be depleted, sealed, or composed of less volatile material. Several researchers have noted that the activity level on 3I Atlas appears unusually strong compared to typical solar system comets. The comet brightened faster than expected as it approached perihelion, suggesting either exceptionally high gas production rates or scattering properties that amplify its apparent brightness. Cryovolcanic jets may be tapping reservoirs of hypervolatile compounds, such as carbon dioxide or carbon monoxide, which sublimate at lower temperatures than water ice and become active farther from the Sun. This interpretation aligns with earlier findings from the James Webb Space Telescope, which revealed an unusually high ratio of carbon dioxide to water in the comet's coma. Carbon dioxide ice reaches sublimation temperatures sooner than water ice as solar heating increases. That early activation would naturally lead to rapid brightening and strong outgassing well before perihelion. Gas dominated by carbon dioxide also expands more energetically than water vapor under similar conditions, potentially driving the intense jet activity now observed. Another possibility builds on the concept of an irradiated crust. During its billions of years in interstellar space, 3I Atlas was exposed to constant cosmic ray bombardment. High-energy particles gradually altered the outer layers of the comet through radiation-driven chemistry, forming a shell of processed material distinct from the pristine interior. This crust could act as a barrier, initially suppressing activity by sealing in volatile compounds. As the comet approached the Sun, heat slowly penetrated this altered layer. When thermal energy finally reached the unprocessed ices beneath, the contrast in physical properties may have produced especially violent eruptions. Pristine interior material, richer in volatiles, would sublimate rapidly once exposed. The boundary between processed crust and untouched ice could also provide natural channels for gas escape. In this model, the comet's structure is primed for sudden activation once a critical thermal threshold is crossed. This framework offers a coherent explanation for the observed timeline. After discovery, 3I Atlas displayed only modest activity for months. Its coma grew gradually as distance decreased. Then, as perihelion approached and heating intensified, activity surged. Cryovolcanic jets may have broken through the irradiated crust, venting material that had been sealed away since before the Sun formed. The comet was not simply warming, it was breaching a shell built during its long interstellar exile. The implications extend beyond this single object. If 3I Atlas is representative, Other interstellar comets may also arrive with radiation-processed crusts that mask their volatile content. Such objects could appear inactive or only weakly active until solar heating penetrates deeply enough. This perspective offers a way to reconcile the behavior of earlier interstellar visitors. Oumuamua showed little visible cometary activity despite exhibiting non-gravitational acceleration consistent with outgassing. A thick irradiated crust could have limited activity to small regions or suppressed it entirely. Borisov, the second confirmed interstellar object, and the first clearly cometary one, did display gas emissions. But its activity was considered muted compared to many solar system comets at similar distances. A partially intact crust could explain that moderation. 3I Atlas appears to represent a more dramatic case. The cryovolcanic eruptions documented in recent weeks suggest that its crust has been breached more extensively. Each eruption removes additional processed material, exposing fresh interior ice to sunlight. New pathways open, and activity escalates, layer by layer. The comet is shedding the shell formed during billions of years between stars. In that sense, 3I Atlas is not just passing through the solar system, it is undergoing a transformation. As it peels away its irradiated exterior, it reveals an interior that has remained hidden since long before Earth existed. What we are witnessing is not evidence of design or intent, but a natural object responding to an extreme change in environment. The physics is familiar, the material is not, and that combination is what makes this interstellar visitor so valuable to study. What is unfolding around 3I Atlas can be understood as archaeology on a cosmic scale. The material now escaping from this object formed in an era we cannot access by any other means. These ices and dust grains condensed inside a protoplanetary disk surrounding a star that may have ceased to exist billions of years ago. Through gravitational interactions that can no longer be reconstructed, the comet was ejected into interstellar space and began a journey that lasted longer than Earth itself has existed. During that time, it passed through regions of the galaxy we have never mapped directly, accumulating radiation damage and undergoing slow chemical change. Now, for a brief interval, those ancient materials are being released in a place where we can observe them. The cryovolcanic jets are the mechanism that makes this possible. Each spiral plume carries molecules from deep within the nucleus into the surrounding coma. Each grain of dust entering that cloud represents a fragment of material formed around another star, a physical remnant of an environment we cannot otherwise sample. These are not samples we can touch or return to laboratories. Instead, they are studied remotely. By analyzing the light they scatter, absorb, and emit. Astronomers can infer composition through spectral fingerprints. Every wavelength carries information, and together those signals allow researchers to reconstruct chemistry, temperature, and structure at a distance. This work continues around the clock as observatories across the world track 3I Atlas. The ice volcanoes remain active, feeding the coma and tails that make the comet such a compelling target. How long this activity will persist is uncertain. The size of the subsurface volatile reservoir is unknown. The internal thermal structure of the nucleus remains poorly constrained. The thickness and continuity of the radiation-processed crust vary from region to region. Each of these factors influences how long eruptions can continue and how intense they will be. What is already clear, however, is that 3I Atlas is offering an observational opportunity unlike that provided by previous interstellar visitors. Its comparatively large size, its volatile rich composition, and its relatively close approach to both the Sun and Earth have combined to create conditions that favor detailed study. The cryovolcanic eruptions are a central part of that opportunity. a reminder that even objects billions of years old can become dynamically active when their environment changes abruptly. Alongside this physical activity, another puzzle has drawn increasing attention. The comet's color does not behave as expected. Early observations showed a reddish appearance, consistent with surfaces enriched in complex organic material that has been altered by long exposure to cosmic radiation. That coloration matched expectations for an interstellar object with an ancient, irradiated crust. Later, as activity increased, the comet began to appear green. That shift immediately raised questions, because the usual explanation for green emission in comets did not seem to apply. The anomaly became especially clear on September 7, 2025. On that night, a total lunar eclipse darkened the sky by removing the moon's glare, creating unusually favorable conditions for observing faint objects. For astronomers studying subtle features, such an eclipse provides a rare advantage. In Namibia, astrophotographers Gerald Riemann and Michael Yeager took advantage of the darkened sky to observe 3I Atlas. The images they captured showed the comet surrounded by a distinct blue-green glow. The coma displayed a coloration that stood out clearly against background stars, extending across roughly 2.5 arc minutes, with a visible tail trailing behind. Under the eclipse conditions, what earlier observations had hinted at became unmistakable. The comet was glowing green. In comets formed within our solar system, a green glow is common and well understood. It is typically produced by a molecule known as diatomic carbon, which consists of two carbon atoms bonded together. Diatomic carbon forms when larger carbon-bearing molecules are broken apart by solar ultraviolet radiation. When these molecules absorb sunlight and re-emit that energy, they fluoresce at specific wavelengths that appear green to human eyes and cameras. This process, called resonance fluorescence, is responsible for the familiar green color seen in many comets as they approach the sun. Under normal circumstances, observing a green coma would be unremarkable. It would simply confirm that standard cometary physics is at work. The problem with 3I Atlas is that spectroscopic measurements tell a different story. Multiple analyses have failed to detect diatomic carbon in significant amounts. A team led by Luis Salazar Manzano at the University of Michigan examined the comet's spectrum and found it to be severely depleted in carbon chain molecules. Both diatomic carbon and related compounds appeared at extremely low levels. By those criteria, 3I Atlas ranks among the most carbon chain depleted comets ever measured. This creates a clear contradiction. Photographs show a green glow, yet spectroscopy indicates that the molecule usually responsible for that glow is largely absent. Either the spectroscopy is missing something, or the green color has a different origin than expected. This tension between datasets is not a flaw in the scientific process. It is often where progress begins. To understand the problem, it helps to consider how spectroscopic measurements work. When astronomers record a spectrum, they are measuring light at specific wavelengths associated with particular molecular transitions. Each molecule produces a unique pattern of emission and absorption lines, effectively a chemical signature. If diatomic carbon were present in large quantities, its characteristic features should appear clearly. Their weakness or absence indicates that the molecule is not abundant in the coma. At the same time, the green color seen in images is real. Cameras sensitive to visible wavelengths consistently record it. Reconciling these observations requires alternative explanations. Several possibilities are under active investigation. One is that diatomic carbon is present, but under conditions that make it difficult to detect spectroscopically while still allowing visible fluorescence. The molecules could be concentrated in thin layers or localized regions of the coma. diluting their spectral signal when averaged over the field of view. Viewing geometry and illumination angle could also affect how strongly emission lines appear. This explanation preserves the standard model but depends on observational complications. A second possibility is that another molecule is responsible for the green emission. While diatomic carbon is the most common source of green fluorescence in comets, it is not the only compound capable of emitting at similar wavelengths. Researchers are examining whether molecules already detected in 3I Atlas, including carbon dioxide, cyanogen, or other organic species, could fluoresce in unexpected ways under the comet's unusual chemical conditions. If so, the green glow would reflect chemistry that differs from that of typical solar system comets. A third explanation shifts focus away from gas chemistry altogether. The color could arise from scattered light rather than fluorescence. If dust grains in the coma have unusual sizes or compositions, they might preferentially scatter green wavelengths. In this scenario, the overall color would be determined by the optical properties of solid particles rather than by emission from gas molecules. This would represent a fundamentally different mechanism and would require detailed study of dust mineralogy and grain size distributions. Distinguishing among these possibilities is not straightforward. It requires spectra taken across multiple wavelength ranges and from different viewing angles. Polarimetric measurements can help constrain dust properties, while thermal emission studies can reveal grain sizes and compositions. Time series observations are also critical, showing how the green color evolves as the comet's activity changes and as solar illumination conditions vary. No single observation can resolve the issue. Only a sustained, multi-technique campaign can narrow the range of explanations. Adding to the complexity, 3I Atlas has not maintained a single color throughout its passage. Shortly after discovery, it appeared red, consistent with a surface dominated by radiation-processed organic material. As activity increased, reports emerged of a shift toward green, suggesting that fresh material exposed by cryovolcanic eruptions might have different optical characteristics than the altered crust. Some observers noted color differences within the coma itself, with inner regions appearing distinct from outer layers. The comet did not present a uniform appearance, but a dynamic one that changed with time and location. Harvard astronomer Avi Loeb suggested a possible link between the color change and a sharp increase in cyanogen production measured by the Very Large Telescope in late August. Cyanogen is a molecule containing carbon and nitrogen that can fluoresce under solar illumination. Its emission typically lies toward violet or blue wavelengths, but interactions with other species could, under certain conditions, shift perceived color. The proposal does not yet provide a complete mechanism, but it highlights how interconnected the comet's chemistry appears to be. The broader chemical context reinforces this view. Observations have identified carbonyl sulfide, a compound rarely detected in comets, along with exceptionally high levels of carbon dioxide. Measurements from ALMA revealed unusually large abundances of methanol and hydrogen cyanide. Together, these findings describe a chemical environment that differs markedly from that of most solar system comets. In such an environment, it would not be surprising for optical behavior to depart from familiar patterns. For now, the green glow remains an open question. It stands as a reminder that even well-established interpretations can fail when applied to objects formed under different conditions. 3I Atlas continues to challenge assumptions, not by violating known physics, but by combining processes and materials in ways we have not previously observed together. As cryovolcanic jets continue to expose new material and as additional data arrive, the comet's color may yet be explained. Until then, It serves as another example of how interstellar visitors expand the range of phenomena that astronomy must be prepared to understand. 3I Atlas does not resemble a typical comet by any simple measure. Its chemical inventory reflects materials that formed under conditions unlike those in our solar system. That difference may be the key to several of the puzzles it presents. The unexplained green glow, for example, may not signal a failure of observation, but a limitation of reference. Our understanding of cometary fluorescence is based almost entirely on objects that formed around the Sun. If 3I Atlas contains compounds that are common around its parent star but rare or absent here, we may lack both the spectral templates and the theoretical expectations needed to recognize them. In that case, the green color would appear mysterious not because it is extraordinary, but because our catalog of known behavior is incomplete. This possibility highlights a humbling reality. Despite centuries of comet observations, decades of spacecraft missions, and thousands of spectra collected across the electromagnetic spectrum, our expertise remains local. We know solar system comets well because they are the only ones we have studied in detail. An interstellar visitor expands the chemical parameter space in ways we are not fully prepared for. It may display optical behavior driven by molecules we have never identified, emitting light at wavelengths we associate with familiar compounds for entirely different reasons. When that happens, color becomes a clue without an immediate explanation. The comet's closest approach on December 19th offers an opportunity to reduce that uncertainty. As 3I Atlas passes within approximately 1.8 astronomical units of Earth, its position relative to our instruments improves significantly. High-resolution spectrographs at major observatories are scheduled to analyze its light with greater sensitivity than at any time since it emerged from solar conjunction. If a specific molecule is responsible for the green emission, its spectral signature may finally be isolated. If the effect instead arises from unusual dust properties, polarimetric and thermal measurements could reveal distinctive mineralogical traits. Either outcome would advance understanding, even if it does not deliver a simple answer. Yet interstellar objects have a tendency to raise new questions as quickly as they resolve old ones. While astronomers continue to investigate the color anomaly, a different class of observations added another dimension to the picture. For the first time, radio astronomers detected emission associated with an interstellar object. These signals did not point toward artificial transmission. They traced chemical processes tied to water and sunlight, revealing activity that could only occur in an icy body responding to stellar heating. On October 24, 2025, astronomers at the South African Radio Astronomy Observatory directed a network of 64 radio dishes toward the region of sky where 3I Atlas was passing through its closest approach to the Sun. This instrument, known as the Meerkat Radio Telescope, operates as a single, highly sensitive antenna capable of detecting extremely faint radio signatures. That night, it recorded absorption features at two well-known frequencies, 1,665 MHz and 1,667 MHz. These frequencies correspond to transitions of the hydroxyl radical, a molecule composed of one oxygen atom bonded to one hydrogen atom and written chemically as OH. When hydroxyl molecules absorb radio waves at these specific frequencies, they imprint narrow absorption lines on the observed spectrum. Meerkat detected precisely this pattern coming from the direction of 3I Atlas. It was the first confirmed radio detection of any interstellar object. Earlier attempts to detect radio emission from 1I Oumuamua and 2I Borisov had produced no such results. In contrast, 3I Atlas proved to be sufficiently active, releasing enough molecular material for radio astronomers to observe. The detection confirmed that water ice was being liberated from the nucleus and then broken apart by solar ultraviolet radiation. It was a historic observation, but also an expected one. The physics involved is well established and entirely natural. When water ice sublimates from a comet's surface, individual water molecules stream outward into space. Solar ultraviolet photons then dissociate those molecules, splitting them into fragments. One of the most common fragments produced by this process is the hydroxyl radical. Although highly reactive and short-lived, hydroxyl persists long enough to absorb and emit radiation at characteristic radio frequencies. The 1665 and 1667 MHz lines are particularly strong and have been used for decades to study comets in our own solar system. Detecting them in 3I Atlas demonstrated that the same photodissociation chemistry applies to interstellar visitors. The timing of the detection was critical. A team led by D.J. Pisano of the University of Cape Town and Oleg Smirnov of Rhodes University had attempted to observe the comet twice before in late September. On those occasions, the comet was farther from the Sun and less active. Water sublimation rates were too low to produce detectable hydroxyl concentrations. By October 24th, solar heating had intensified enough to drive stronger outgassing. The third attempt succeeded because the comet had entered a more energetic phase of its evolution. The observation also benefited from geometry. At the time, 3I Atlas lay close to the Sun's position in the sky as seen from Earth, a configuration known as solar conjunction. While this might seem disadvantageous, the comet's high velocity relative to Earth produced a Doppler shift that moved the hydroxyl absorption lines away from frequencies dominated by solar or terrestrial interference. The result was a clean detection against the background. Given the long-standing association between radio signals and the search for extraterrestrial intelligence, some observers were quick to speculate. Radio astronomy has played a central role in efforts to detect technological emissions, and famous events such as the 1977 WOW signal remain part of public memory. The fact that 3I Atlas arrived from a region of sky within roughly 9 degrees of that earlier signal only added fuel to speculation. Could the radio detection represent something artificial? The answer is unambiguous. The hydroxyl absorption lines observed by Meerkat match known molecular transitions exactly. Their frequencies, line widths, and timing are consistent with thermal broadening and excitation conditions expected for a cometary coma. The signal appeared precisely when increased water sublimation would predict it. There is no aspect of the detection that suggests an engineered origin. Instead, it provides strong evidence that 3I Atlas is an icy, volatile rich body responding naturally to solar heating. In fact, the radio detection resolves one of the concerns raised earlier in the comet study. Some observers noted that 3I Atlas appeared dominated by carbon dioxide rather than water, raising questions about whether it was truly cometary in nature. The presence of hydroxyl confirms that water ice is indeed part of its composition and is being actively released. The radio signature represents ancient water ice from another star system sublimating for the first time in the warmth of our Sun. At the same time, the detection revealed something unexpected about the rate of water loss. Even at a distance of roughly 1.38 astronomical units from the Sun, where surface temperatures would be lower than Earth's by about 15%, the comet was shedding water molecules at a substantial rate. Many solar system comets show only modest water activity at such distances, with sublimation increasing sharply closer to the Sun. The elevated activity in 3I Atlas suggests differences in physical properties. One possibility is low thermal inertia, if heat penetrates the comet's surface more efficiently than in typical comets. Subsurface ice could warm and sublimate at greater distances. Another possibility is the presence of pockets of unusually pure water ice that respond readily to moderate heating. A third explanation involves interaction with carbon dioxide outgassing. Strong carbon dioxide flows could entrain water ice grains, carrying them away from the nucleus before they fully sublimate. Each mechanism is plausible, and more than one may be operating simultaneously. Researchers are also interested in what the hydroxyl detection might reveal about the comet's original environment. Isotopic ratios in water, particularly the ratio of hydrogen to deuterium, encode information about the temperature and conditions under which the ice formed. In solar system comets, these ratios vary depending on formation region within the protoplanetary disk. Measuring them in 3I Atlas could offer rare insight into the disk surrounding its parent star. Unfortunately, the Meerkat observations did not have sufficient sensitivity to determine isotopic ratios. The absorption lines confirmed presence but lacked the precision required for that level of analysis. Future observations with other facilities may succeed, especially if the comet remains active as it moves outward. In early November, radio astronomers also conducted a different kind of search. On November 5th, Meerkat observed 3I Atlas using a system designed to identify narrow-band radio transmissions associated with technology. This instrument, developed for the Breakthrough Listen initiative, examined frequencies from 900 MHz to 1,670 MHz, scanning for coherent signals unlike those produced by natural processes. The result was negative, but informative. More than 23,000 candidate signals were detected during the observation, all attributable to human-made radio frequency interference. None matched the comet's position in a way that would indicate transmission from the object itself. The analysis placed an upper limit on any potential technological emission of approximately 0.17 watts across the observed frequency range. At the comet's distance, this is comparable to the power output of a mobile phone handset. If 3I Atlas were transmitting at higher power levels in these bands, it would have been detected. These findings constrain, rather than fuel, speculation. They demonstrate that no detectable artificial radio emission accompanies the comet. Some have suggested that future spacecraft, such as Juno during its operations near Jupiter in March 2026, could search for lower frequency emissions outside Meerkat's range. Such proposals reflect continued curiosity rather than evidence. What the current data show is clear. Across optical, infrared, X-ray, and now radio wavelengths, 3I Atlas behaves as a natural object governed by known physical processes. At the same time, it continues to stretch those processes into unfamiliar regimes. Its chemistry is unusual. Its activity is intense. Its behavior unfolds in ways that challenge assumptions built on solar system examples alone. Each new observation adds clarity while expanding the scope of what must be explained. In that balance between confirmation and surprise lies the true scientific value of this interstellar visitor. The radio record of 3I Atlas now tells a clear and balanced story with two distinct threads. One is firmly grounded in natural science. The detection of hydroxyl absorption confirms that this object is an icy comet, undergoing the same photodissociation chemistry observed in comets native to our solar system as they interact with sunlight. The second thread addresses a different question entirely. Dedicated searches for artificial radio emissions have produced negative results, ruling out obvious technological signals within the frequencies and sensitivities examined so far. Together, these threads help define what 3I Atlas is, and just as importantly, what it is not. There is However, one additional radio-related claim that must be addressed carefully. In late November and early December, reports began circulating about unusual radio features allegedly associated with 3I Atlas. According to these claims, signals appeared at specific frequencies, with timing and frequency drift that seemed consistent with a moving object, yet did not match standard expectations for cometary radio behavior. These reports attracted attention precisely because they sounded anomalous. At present, they remain controversial and unverified. They have not been independently confirmed by major radio observatories, nor have they appeared in peer-reviewed publications. Experience in radio astronomy shows that instrumental effects, terrestrial radio frequency interference, and data processing artifacts can easily generate spurious signals that seem mysterious until they are carefully analyzed. For this reason, the scientific community has withheld judgment and is waiting for rigorous verification before drawing conclusions. What can be stated with confidence is that 3I Atlas has already made history in radio astronomy. It is the first interstellar object ever detected at radio wavelengths. The hydroxyl signature demonstrates active water chemistry. The potential for isotopic measurements remains open for future observations. The targeted search for technological emissions found nothing above well-defined limits. These results anchor discussion in evidence, even as speculation continues at the margins. As the December 19th flyby approaches, tension has increasingly shifted beyond chemistry and emissions to a different kind of question. It is a question about motion rather than composition. Specifically, it concerns the trajectory 3I Atlas is following through the solar system. Harvard astrophysicist Avi Loeb has drawn attention to what he describes as an extraordinary coincidence in the comet's future path. In March of 2026, 3I Atlas is predicted to pass Jupiter at a distance that closely matches the boundary of the planet's gravitational sphere of influence. Loeb estimates the probability of such an alignment occurring by chance to be roughly 1 in 26,000. He asks whether this should be interpreted as coincidence or as something more precise. To understand why this has attracted attention, it is necessary to explain what that boundary represents. Every massive body in space exerts gravitational influence, but that influence competes with the gravity of other bodies, especially the Sun. The Hill radius defines the region around a planet within which the planet's gravity dominates over the Sun's and can retain moons or capture passing objects. Inside this region, the planet is the primary gravitational authority. Outside it, solar gravity prevails. For Jupiter, the Hill radius is approximately 53.5 million kilometers. Current orbital calculations predict that on March 16, 2026, 3I Atlas will pass at a distance of about 53.6 million kilometers from Jupiter, with an uncertainty of roughly plus or minus 60,000 kilometers. The difference between the predicted closest approach and the Hill radius is therefore on the order of 100,000 kilometers, less than 1% of the total distance. In a solar system where encounters often differ by millions or billions of kilometers, this is a notably tight alignment. Loeb frames this in practical terms. If one were deliberately designing a trajectory to reach the edge of Jupiter's gravitational domain, it would be difficult to choose a better path. He argues that if the trajectory were random, the probability of landing so close to that specific boundary would be low. Though not impossible, unlikely events do occur in a universe of enormous scale. Still, the alignment is unusual enough, in his view, to merit scrutiny. The significance of this location becomes clearer when considering orbital mechanics. Near a massive body, an object's velocity is high. This is the regime where what engineers call the Oberth effect becomes important. named after the spaceflight pioneer Hermann Oberth. This effect describes how a propulsive burn performed at high speed near a massive body yields a greater change in orbital energy than the same burn performed farther away. Space missions routinely exploit this principle to maximize efficiency. In a hypothetical technological scenario, an object approaching Jupiter's Hill radius could take advantage of this region to deploy smaller probes into bound orbits around the planet with minimal energy expenditure. Those probes could remain within Jupiter's gravitational influence, potentially occupying stable locations such as Lagrange points, where long-term orbital maintenance requires little fuel. This scenario, as Loeb emphasizes, is speculative. It is not supported by direct evidence. It is a thought experiment illustrating why the specific location of the flyby has drawn attention. Against this, the empirical record remains straightforward. Every observation of 3I Atlas so far, from its chemical composition to its dust and gas activity to its radio emissions, is consistent with a natural interstellar comet responding to solar heating. The Jupiter alignment is striking, but coincidence alone does not constitute evidence. Drawing extraordinary conclusions from trajectory data in isolation would not meet scientific standards. Loeb nonetheless argues that the trajectory should be considered alongside other features he describes as anomalies. He notes that the comet's path is closely aligned with the ecliptic plane of the solar system, an orientation he estimates would occur with a probability of about 0.2% for a randomly arriving interstellar object. He points out that its arrival direction lies within roughly 9 degrees of the location associated with the 1977 WOW signal, which he assigns a probability of about 0.6%. He also highlights the timing that brought the comet relatively close to Mars, Venus, and Jupiter, while rendering it unobservable from Earth during perihelion, which he estimates at about 0.005% probability. Individually, each of these features might be dismissed as unremarkable. Combined, Loeb argues, they yield a probability of less than 1 in 100 million if the object is purely random. This line of reasoning has drawn criticism from many astronomers. The calculation depends strongly on assumptions about what constitutes the appropriate comparison set. Selecting features after they are observed and labeling them anomalies can inflate improbability. In a universe containing countless objects, some will inevitably display unusual combinations of properties by chance alone. There is also the problem of sample size. Humanity has identified only 3 confirmed interstellar objects to date. Attempting to derive meaningful statistics from 3 data points is inherently risky. Patterns inferred from such a small sample may not reflect the true distribution of interstellar visitors. Loeb acknowledges these objections, but maintains that the potential implications justify continued attention. He frames the issue in terms of risk rather than likelihood. If 3I Atlas is a natural comet, further study enriches planetary science and astrobiology. If, however, it were technological in origin, the consequences for humanity's understanding of its place in the universe would be profound. Protocols for response, communication, and planetary defense would all require reconsideration. Loeb describes this as a version of Pascal's wager applied to extraterrestrial intelligence. Even a low probability might warrant investigation if the stakes are high. In response, Loeb has called for intensified monitoring as the comet continues its journey. He has suggested searches for low-frequency radio emissions beyond those already examined, careful tracking for unexpected changes in trajectory, and high-resolution imaging of the nucleus and surrounding structures. He has proposed that the Juno spacecraft, which will be operating near Jupiter during the March 2026 encounter, should be used to search for signals or anomalies as the comet approaches the planet. The broader scientific community has reacted with a range of views. Some astronomers reject the alien hypothesis outright, arguing that it distracts from the genuinely rich natural science 3I Atlas offers. Others take a more measured position. The search for extraterrestrial intelligence is a legitimate scientific endeavor, and interstellar objects are, in principle, a category where artificial probes could appear. Dismissing the possibility without examination would not be scientific either. What unites these positions is agreement on method. Hypotheses must be tested against evidence. If 3I Atlas continues to behave as a comet should as it recedes from the Sun, the case for natural explanation strengthens. If it were to exhibit behavior that cannot be explained by known physics, the situation would change. There are clear criteria for what would qualify as genuinely unexpected. A sudden change in trajectory that cannot be attributed to outgassing or gravitational interactions would demand explanation. Detection of a coherent radio signal with characteristics inconsistent with natural processes would be significant. Observation of objects being deliberately released from the nucleus would be significant. Structural features visible in high-resolution imaging that defy natural interpretation would also be significant. To date, none of these have been observed. As it stands, 3I Atlas looks like a comet, behaves like a comet, and exhibits the chemical and physical signatures of an icy body from another star system responding to solar heating. The upcoming passage near Jupiter provides a concrete, testable milestone. Continued astrometric measurements will refine the trajectory and either confirm the precise alignment with the Hill radius or show that uncertainties made the coincidence appear more exact than it truly is. Spacecraft and ground-based observatories will be watching. If nothing unusual occurs, the natural interpretation will emerge stronger than before. If something does occur, it will be captured by multiple independent instruments and subjected to careful analysis. Either outcome advances knowledge. In that sense, the Jupiter flyby is not a moment of revelation, but a rigorous experiment conducted by the solar system itself. With 3I Atlas as the test particle and evidence as the final arbiter, the broader context matters because interstellar travel is no longer a theoretical idea limited to science fiction. Humanity has already launched technological objects onto trajectories that will eventually leave the solar system entirely. Spacecraft, such as the Voyager probes, are now drifting toward other stars, carrying physical records of their origin in the form of engraved messages. In billions of years, those objects will pass through alien planetary systems. If they are detected by intelligent observers elsewhere, those observers will face the same question we now confront with 3I Atlas. Is this object natural? Or is it artificial? The fact that humanity has already done this establishes an important baseline. The idea that technological artifacts could exist on interstellar paths is not absurd. It is demonstrably possible. If one young technological civilization can send objects between the stars, then older civilizations could, in principle, have done the same long before us. For that reason alone, the hypothesis that some interstellar visitors might be artificial cannot be dismissed out of hand. It is not a philosophical claim. It is an empirical question, one that can only be addressed through careful observation. At the same time, assuming an answer before the evidence is complete would be unscientific in either direction. Declaring that 3I Atlas must be artificial ignores the strong body of data pointing toward natural cometary processes. Declaring that it must be natural closes off legitimate inquiry prematurely. The responsible position lies between those extremes. At present, the evidence overwhelmingly supports a natural origin. while a smaller set of unusual features motivates continued scrutiny rather than premature conclusions. As December 19th approaches and the comet reaches its closest distance to Earth, observers have their best opportunity to examine it in detail. High-resolution spectroscopy may reveal additional molecular species. Imaging may resolve finer structures within the coma and jets. Astrometric measurements will continue to refine predictions for the Jupiter encounter. Each new observation adds information. And information is the only reliable path from speculation to understanding. Within this context, the jets emerging from the nucleus have drawn particular attention. Avi Loeb has highlighted certain jet features that he argues are difficult to reconcile with standard comet models. Some jets do not simply trail away from the sun, as might be expected. Instead, several appear oriented roughly perpendicular to the solar direction. And at least one has been reported extending ahead of the comet rather than behind it. If such features are real and persistent, and not artifacts of imaging or geometry, they would require explanation. This brings the discussion to the jets themselves. In the days following 3I Atlas's re-emergence from behind the sun, observers documented plume structures stretching across millions of kilometers. These were not diffuse clouds that faded quickly into the surrounding coma. They appeared as focused streams, maintaining coherence over distances longer than many models would predict for simple sublimation-driven outflows. Their orientation, in some cases, did not align neatly with expectations based solely on solar heating. The standard model of cometary jets is well established. Solar radiation warms volatile rich regions on the comet's surface. Once sublimation begins, gas escapes, dragging dust along with it, because the sun is the energy source. Activity tends to concentrate on illuminated regions. Radiation pressure and the solar wind then shape the escaping material, producing jets and tails that generally point away from the sun or curve in that direction as they evolve. 3I Atlas has shown jets that complicate this picture. Multiple independent images show plume-like features extending roughly perpendicular to the Sun-comet line. At least one structure appears sunward, forming what observers sometimes call an anti-tail. Anti-tails are not unknown in cometary science, but they are uncommon and strongly dependent on viewing geometry. Their appearance here has naturally drawn attention. Loeb has interpreted these features as potentially consistent with directional control, suggesting that such jets could represent propulsive exhaust or a deliberate mechanism for clearing a path through interplanetary dust. In this speculative framework, the jets would not merely be byproducts of heating, but tools for maneuvering or protection. Most comet scientists offer alternative explanations rooted in well-understood physics. Comet nuclei are irregular bodies with uneven surfaces, complex topography, and heterogeneous composition. Active regions can exist anywhere on the surface, not just at the point facing the sun. As the nucleus rotates, jets from fixed surface locations sweep through space, creating changing orientations over time. A jet that appears perpendicular to the sun at one moment may align more conventionally at another phase of rotation. Projection effects also play a significant role. When a comet's tail lies close to the observer's line of sight, three-dimensional structures can appear distorted in two-dimensional images. Material moving away from the sun can seem to point toward it. Depending on geometry, similar visual illusions occur routinely in astronomy and even in everyday experience. Determining the true orientation of a jet requires observations from multiple times and, ideally, multiple viewpoints. In addition, cometary jets are not simple ballistic streams. Ionized gas interacts with magnetic fields carried by the solar wind. Dust grains respond differently to radiation pressure depending on their size and composition. These forces can reshape outflows in ways that are not immediately intuitive. A feature that appears tightly collimated in visible light may look broader or more diffuse at other wavelengths. Proper interpretation requires detailed modeling that incorporates gas dynamics, dust physics, electromagnetic effects, and solar conditions. Another layer of complexity comes from the apparent pulsation of some jets. Time series images show features that brighten and fade in repeating cycles, giving rise to what some have called a heartbeat pattern. The most straightforward explanation is rotational modulation. As the nucleus spins, active vents move into and out of sunlight. A vent located near the equator of a nucleus with a rotation period of several hours would experience regular heating cycles, producing periodic outbursts. The resulting pattern in images would naturally resemble a pulse. Loeb has suggested that if the timing of these pulses does not match any plausible rotation period, the behavior would deserve closer attention. So far, analyses indicate that the observed variations are consistent with rotational effects, though uncertainties remain due to limited data and complex jet geometry. Additional observations are needed to constrain the rotation period more precisely. Determining whether the jets are unusual in a fundamental sense requires a systematic approach. Astronomers must measure the rotation period of the nucleus through photometric light curves. They must identify active regions through high-resolution imaging and track how jets evolve over time. They must compare observed jet orientations with predictions from models that incorporate rotation, surface geometry, and solar forcing. Only by matching theory to observation can genuine anomalies be identified. At present, the data are consistent with natural explanations. Spiral jet patterns documented by European observers match models of material ejected from a rotating body. The bright coma captured by spacecraft imagery reflects intense outgassing near perihelion. The presence of both dust and ion tails aligns with standard comet behavior. No observation so far requires invoking artificial mechanisms. This does not diminish the scientific value of the jets. On the contrary, they offer a rare opportunity to study how interstellar comets differ from those formed in our own solar system. 3I Atlas appears unusually rich in carbon dioxide, a volatile that sublimates at lower temperatures than water ice. Jets dominated by carbon dioxide may expand differently, producing higher velocities and stronger collimation than water-driven jets, typical of local comets. The internal structure of the comet may also be highly patchy. Regions with different compositions could vent at different times, creating multiple jets with distinct properties. An ancient irradiated crust may fracture unevenly as solar heating penetrates, leading to localized cryovolcanic eruptions rather than uniform activity. These jets provide a window into the interior. Different volatile species sublimate at different temperatures. Early activity is dominated by hypervolatiles such as carbon dioxide. As heating progresses, water ice becomes increasingly important. By tracking how jet composition changes with distance from the sun, researchers can infer the layering of the nucleus and the distribution of volatiles within it. For an interstellar object, this information is especially valuable. 3I Atlas formed in a protoplanetary disk with unknown temperature gradients and chemical conditions. The layered structure of its nucleus preserves a record of those ancient environments. Each jet effectively extrudes a sample from a specific depth, turning the comet into a natural probe of another star system's formation history. Even the degree of collimation carries information. Highly focused jets imply narrow vents or constrained subsurface cavities. Observing such features allows scientists to infer aspects of internal morphology that would otherwise be inaccessible at interstellar distances. In this sense, the jets are not merely visual curiosities. They are diagnostic tools. Taken together, The jet behavior of 3I Atlas reinforces a broader theme. This object is not extraordinary because it defies physics, but because it allows us to test physics under conditions we have never directly observed before. It is an interstellar laboratory, revealing how icy bodies formed around other stars respond when they encounter a new sun. The jets are one more chapter in that story, carrying information outward, molecule by molecule, from a place we will never visit to a vantage point where we can finally study it. Some researchers have suggested that the unusual jet behavior of 3I Atlas may arise from a combination of its composition and its extreme thermal history rather than from any exotic cause. An object that spent billions of years in deep interstellar cold is expected to develop an outer crust that has been heavily altered by cosmic radiation. This irradiated layer would differ physically and chemically from the pristine ices preserved deeper inside the nucleus. When 3I Atlas entered the inner solar system and solar heating began to penetrate that crust, pressure gradients would have formed between the altered exterior and the volatile-rich interior. In this picture, the crust acts less like a porous sponge and more like a sealed lid. Gas does not seep out gradually across the surface. Instead, it accumulates beneath the crust until pressure exceeds the mechanical strength of the overlying material. When that threshold is crossed, the release is sudden and concentrated, venting through localized weaknesses such as fractures or thinner regions. The result would be short-lived but powerful eruptions rather than steady outflow. Jets produced this way could appear unusually vigorous and tightly focused. Their directions would depend on where the crust fails, not necessarily on where sunlight is strongest. Their timing would depend on how quickly pressure rebuilds after each release, which may or may not align with the rotation period of the nucleus. This pressure release model offers a natural explanation for several observed features at once. It accounts for the strength of the jets, their apparent intermittency, and their sometimes unexpected orientations. Testing this idea requires detailed monitoring of jet evolution over time, following individual features as they emerge, expand, and fade. The period around closest approach to Earth offers the best opportunity for such observations. High-resolution imaging from the Hubble Space Telescope and from ground-based telescopes equipped with adaptive optics may be able to capture jets at the moment of formation, placing constraints on eruption mechanisms that have never before been available for an interstellar object. Regardless of how the jet physics ultimately resolves, the activity itself is reshaping 3I Atlas in real time. Every kilogram of gas and dust expelled into space is mass lost permanently. The nucleus is eroding continuously, particle by particle and molecule by molecule. The very processes that make the comet bright and scientifically valuable are also the processes that are dismantling it. By the time 3I Atlas leaves the solar system, it will be measurably smaller than when it arrived. This raises a question about the comet's long-term future. After departing the planetary region, 3I Atlas will coast outward into interstellar space and cool once again as solar heating fades. It will wander for millions or billions of years. Will it retain enough volatile material to become active again if it passes close to another star in the distant future? Or has this encountered depleted reservoirs that cannot be replenished? There is no way to know. What can be known is how much material is lost during this passage. And that loss can be documented while observation remains possible. The calendar matters. The closest approach on December 19th marks a turning point. Before that date, the comet grows brighter and easier to study. After it, distance increases steadily. Each additional kilometer weakens the signal. Each passing week dims the coma. Each month pushes the object closer to the limits of our instruments. The window that opened when the comet was first detected in July will gradually close. And eventually, 3I Atlas will fade back into interstellar darkness, indistinguishable from the countless other objects drifting between stars. Observation does not end on December 19th, but it changes character. The focus shifts from capturing peak activity to documenting decline and preparing for the next major milestone in the comet's journey. The James Webb Space Telescope has observations scheduled to track how the carbon dioxide-dominated coma evolves as the comet moves away from the Sun, near perihelion. Solar heating drove carbon dioxide sublimation at extreme rates. As distance increases and temperatures fall, that activity should decrease in a predictable way. Webb's measurements will test whether the decline follows established physical models or deviates from them. Radio observatories, including ALMA, will continue monitoring methanol and hydrogen cyanide production. Power law relationships, measured before perihelion, predict how these production rates should drop with increasing distance. Confirming those predictions would strengthen confidence in current models of the comet's volatile inventory. Deviations would point to unexpected internal structure or chemistry. Ground-based telescopes will track the fading light curve night after night. They will document changes in coma shape as jets weaken and disappear. They will measure spectral lines and colors, looking for shifts as different volatile species freeze out at different temperatures. Together, these observations will form a continuous record from discovery through departure. By January of 2026, 3I Atlas will be more than 2 astronomical units from the Sun, roughly the distance of the asteroid belt. Activity should be greatly reduced. By February, the full dataset from the JUICE spacecraft's November observations will finally arrive, providing close-range measurements that complement the more distant monitoring. Researchers will spend months analyzing those data, comparing them with results from Webb, Hubble, and ground-based observatories to reconstruct the comet's behavior during its most active phase. Then comes March 16th, 2026. When 3I Atlas passes near Jupiter at a distance of about 53.6 million kilometers, essentially grazing the boundary of the planet's gravitational sphere of influence from Earth. The comet will be faint, but still trackable through precise astrometry. Any deviations from predicted motion caused by gravitational interactions or asymmetric outgassing should be detectable. There has been discussion about whether the Juno spacecraft, currently orbiting Jupiter, might observe the comet during this encounter. Juno's instruments operate at radio frequencies inaccessible from Earth, ranging from tens of hertz to tens of megahertz. If any low-frequency emissions were present, Juno would be uniquely positioned to detect them. Whether such observations will be scheduled remains uncertain. Juno has primary scientific objectives focused on Jupiter, and reallocating resources for a speculative search is not trivial. Still, the opportunity is singular. No other spacecraft will be in position to observe 3I Atlas at Jupiter range. After the Jupiter encounter, the comet will accelerate outward. By late 2026, it will cross Neptune's orbit. By the end of the decade, it will be beyond the Kuiper Belt, still moving at roughly 130,000 miles per hour, still carrying whatever information it has not yet released. Eventually, it will fade beyond detectability altogether. The encounter itself will be brief, but its scientific impact will be long-lasting. The data collected over these months will be analyzed for years, perhaps decades. Future researchers will revisit the archive with new tools and new questions. 3I Atlas will become a reference point for interpreting future interstellar visitors. This matters because interstellar objects are not rare accidents. Models predict that thousands pass through the solar system at any given time. most too small or too distant to detect. The fact that 3 have been found in less than a decade suggests that the population is substantial. As survey telescopes improve and sky coverage becomes more complete, more such objects will be discovered. Each will carry material from a different star system. 3. I-Atlas is special because circumstances aligned. It is large, active, and passed close enough to study in detail. Earlier visitors were smaller, fainter, or discovered too late. There is no guarantee the next one will be as favorable. It may arrive faster, fainter, or on a trajectory poorly suited for observation. 3. I-Atlas represents an opportunity that was recognized and acted upon. As it continues outward, some of its signatures may persist for a time. The X-ray halo detected earlier may still glow faintly. The twin tails may still stream behind the nucleus, though shorter and less defined. The green emission that puzzled observers may linger as activity declines. Methanol and hydrogen cyanide will continue venting until their sources are exhausted. Within that shrinking envelope lies a frozen record of another star's protoplanetary disk, material that formed perhaps 7 billion years ago. What has been learned so far is substantial: carbon dioxide and water, methanol and hydrogen cyanide, nickel, cyanogen, X-rays, radio absorption, twin tails, spiral jets, and unexplained green emission all form parts of a coherent picture, not a picture of an object that violates physics, but of one that formed elsewhere and reveals how diverse planetary systems can be. 3. I-Atlas arrived, was studied, and will depart. Indifferent to the attention it received, the significance lies not in the object itself, but in what its passage reveals about the universe and about our ability to learn from brief encounters with the unknown.